Today we're going to talk about instrumentation amplifiers. Now, where do we use instrumentation amplifiers? They say instrumentation amplifiers are commonly used in environments with high common mode noise, such in data acquisition systems where remote sensing of input variables is required. If you go and think in industry, what do they have? They got a plant where they control certain processes, and then they're sensing a lot of information from the plant, and that goes via cables to a control room where everything is done and everything is checked and controlled from. But due to these long cables, there's a lot of noise. We know in industry, there's electricity, there's a lot of noise. And to basically get rid of this noise, we're going to look at the instrumentation amplifier, because that's going to help us to get rid of noise, especially where you want to amplify small signals, because some of these sensing units will normally give you out small signals. And that brings us to the basic instrumentation amplifier. They say an instrumentation amplifier is a differential voltage gain device that amplifies the difference between the voltage existing at its two input terminals. The main purpose of an instrumentation amplifier is to amplify small signals that may be riding on a large common mode voltages. I've told you we're going to amplify small signals. We are going to amplify small signals. The key characteristics are high input impedance, high common mode rejection, low output offset, and low output impedance. That is the main characteristics of this instrumentation amplifier. The basic instrumentation amplifier is an integrated circuit that internally has three operational amplifiers and several resistors. The voltage gain is usually set by an external resistor. You see here, you can put an external resistor, and that's the gain setting resistor. The basic instrumentation amplifier is shown in figure 14.1. Op-amps A1 and A2 are non-inverting configuration that provide high input impedance and voltage gain. Op-amp A3 is used as the unity gain differential amplifier with high precision resistors that are all equal in value. All right, there you can see the high precision resistors R3, R4, R5, and R6. That means they got very small tolerances. They say the gain setting resistor RG is connected externally, as I already mentioned. Here we put our gain setting resistor RG, that's externally. As shown in figure 14.2, we'll have a look at figure 14.2. Op-amps A1 receives the differential input signals V in 1 on its non-inverting input and amplifies the signal with a voltage gain of AV is 1 plus R1 divided by RG. That is the voltage gain for that. All right, here they show us RG. There's my gain setting resistor. And you can see if I look at the input, I will have V in 1 plus the common mode signal, and I will have V in 2 plus the common mode signal. The common mode signal will normally be the large signal. The input V in 1 and V in 2 will be my small signals. That's the signals I actually want to amplify, and that's the information I want. That means the output will be the closed loop gain of V in 2 minus 1. That means we will get rid of the common mode signal. They say op-amp A1 also has V in 2 as an input signal to its inverting input through op-amp A2 and the power formed by R2 and RG. The input signal V in 2 is amplified by op-amp A1 with a voltage gain of AV is equal to R1 divided by RG. The overall closed loop gain of the instrumentation amplifier is there's a closed loop gain, 1 plus 2R divided by RG. They say where R1 is equal to R2 is equal to R. Equation 14.1 shows that the gain of the instrumentation amplifier can be set to a value of the external resistor RG when R1 and R2 are known fixed values. See Appendix B for the derivation. All right, you don't have to worry about the derivation. We will just look at the final gain. They say the internal gain setting resistor RG can be calculated for desired voltage gain by using equation 14.1. They say RG is equal to 2R divided by the closed loop gain minus 1. Instrumentation amplifiers which a gain is set to specific values using a binary input instead of a resistor are also available. All right, we're going to have we will look at specific instrumentation amplifiers. They will give us standard values. They say in example 14.1, determine the external gain setting resistor RG for a certain IC instrumentation amplifier when R1 is equal to R2 is equal to 25 kilo ohm. The closed loop gain to be 500. All right. Then we can work out the value of RG. It's equal to 2R divided by the closed loop gain minus 1. That means 2 times R. R was given as 25 kilo ohms. That means 2 times that will give me 50 kilo ohms divided by 500 minus 1. And that will give me a gain setting resistor of 100. All right. That means if I apply a gain setting resistor of 100, then I will have a closed loop gain of 500. All right. Just to point out what we were talking about. If we look at our signals and we look at the instrumentation amplifier, this is the common mode signal. That means the signal I want to amplify, V in 1, will be basically this small signal riding on the common mode signal. And V in 2 will be that small signal riding also on the common mode signal, right? Now, when you put it through the instrumentation amplifier, it will get rid of the common mode signal and only amplify the difference between V in 1 and V in 2, all right? You see here, they tell us here, small difference in high frequency signal riding on a large low frequency common mode signal, instrumentation amplifier, and amplify the differential signal, no common mode signal, all right? That's basically, we want to get rid of the common mode signal. And the common mode signal will normally be, in our case, around about a 50 hertz signal. It's going to be quite a low frequency, while my signal I want to amplify is going to be a much higher frequency. Now we're going to look at specific instrumentation amplifiers. That means that you can buy, that certain guys is manufacturing, or companies is manufacturing. Now here we're going to look at the AD622. That means you can go to an electronic shop and ask them and can buy a instrumentation amplifier, AD622 instrumentation amplifier. And here they give us all the information, all the pin connections. They say now you have a basic idea how an instrumentation amplifier works. Let's look at a specific device. A representative device, the AD622, is shown in figure 14.4, where the IC pins are given for reference. The instrumentation amplifier is based on the design using 3 op amps that was shown in figure 14.1. All right. You can see here, there is my one input, my other input, my gain setting resistance, my positive supply, my negative supply, my output, and my reference. They say some features of the AD622 are as follows. The voltage gain can be adjusted from 2 to 1000 with the external resistor RG. There is unity gain with no external resistor. That means if I don't apply anything to these terminals, it will have unity gain. That means then it will have a gain of 1. All right. The input impedance is 10 giga ohm. That means we've got a fairly high input impedance. the common mode rejection ratio has a minimum value of 66 dBs. Recall that the higher the common mode rejection ratio means better rejection of the common mode voltages. They say the AD622 has a bandwidth of 800 kilohertz at a gain of 10 and a slew rate of 1.2 volt per microsecond. You know about bandwidth, you know about slew rate. Now let's quickly have a look at setting the voltage gain. They say setting the voltage gain for an AD622, an external resistor must be used to achieve voltage gain greater than unity as indicated in figure 14.5. Resistor RG is connected between RG terminals pins 1 and 8. No resistors required for unity. RG is selected for the desired gain based on the following formula. That's the basic formula. And here they say RG is equal to 50,5 kilo ohm divided by AV minus 1. That means that 50,5 kilo ohm is a constant value. All right. They say notice that the formula is the same as equation 14.2 for the 3 op-amps configuration with the external RG, where the external resistors R1 and R2 are each 25,25 kilo ohm. In the previous example, we used 50 kilo ohms, but for this device, it's 25,25. That's why it will give me 50,5 kilo ohm. All right. That is standard for that device. That means if you're going to use the AD622, you're going to use 50,5 kilo ohms. All right. Just remember. Yeah, they also just show us the pin connections. They show us the pin connections, they show us where we connect RG, my 2 inputs, and my supply, and my output, and my reference. All right. Then they give us gain versus frequency, basically the frequency response of this device. If we look at the frequency response, you will notice the higher the gain, the smaller the bandwidth. If you go and look at the gain of 1,000, you will have a much smaller bandwidth. If we go and have look at unity gain, you will notice your bandwidth will increase a lot. All right. That higher gain, smaller bandwidth. Lower gain, larger bandwidth. Let's have a look at this example. Example 14.2. They say, calculate the voltage gain and determine the bandwidth using the graph in figure 14.6 for the instrumentation amplifier in figure 14.7. All right. They give us the supply plus 15 minus 15 volts. My inputs, I got a gain setting resistor there of 510 ohms. And they want us to calculate the voltage gain. That means we're going to use that formula and we're going to use 50,5 because that's AD622. All right, there's the formula. RG is equal to 50,5 kilo ohm divided by AV minus 1. We want AV, and when we work out AV, we will get a gain of 100. All right. Now let's quickly talk about this approximate bandwidth. I differ a little bit from the book. Let's go and have a look. We now know our gain is equal to what? 100. All right. Now if we go back to this graph, yeah. That means which curve are we going to use? We're going to use this curve because there's my gain is 100. But now if you're going to look at your bandwidth, you normally take it how many dBs down? Minus 3 dB or 0.707 of the maximum. That means it will look to me around about there. If I look at there it will cut the curve. It will look to me around about 100K. Now, what do they tell you in the book? They tell you 80K. You know, I don't agree. But if I ask you a question like that, I will make sure you will give me the correct answer. All right. They say approximate. Now, if you look at the newer books, then they talk about, some books they talk about 60 kilohertz, and then they move it to 80 kilohertz. I don't agree completely. That means I will say it's closer to 100 kilohertz according to me. All right. But you must know, you must use the right graph. You must first go and calculate the voltage gain, and when you know the voltage gain, you can go and find your bandwidth. All right. All right, then we're going to talk about effects of noise in instrumentation amplifier applications. All right, I'm not going to read through all this. Let's quickly going to have a look what's going to happen. Now, we know if we got long transmission lines, that means I've told you, you got the plant and you got your control room. Now, these things can be, let's say, a kilo from one another. Normally, the control room is quite far from your plant. Now, these cables are running, and when cables are running parallel to one another, what happens? There will be a very small capacitance, all right? That means between those cables, there's going to be small capacitance, all right? Now, what will happen? Due to this capacitance, it will actually create a phase shift, all right? That means my common mode signal is not going to be 100% in phase, all right? And now, due to that phase shift, it's going to cause that we don't going to basically will have complete elimination of my common mode signals, all right? And now, that is one of the problems, and that will bring us to shield guard, because with shield guard, we can basically eliminate that problem, all right? All right, here they apply shield guard. Now, we know what is the characteristics of a voltage follower. What's the characteristics of a voltage follower? All right, got very high input impedance, got very low output impedance, and it got unity gain. All right. Now, we put a voltage follower in here, and we make it basically adjustable, and by doing that, we can get these common mode signals 100% in phase, all right? And that's why they say effect of straight disturbed capacitance is effectively cancelled, and we can cancel it out. Then we will have complete common mode rejection. All right. You with me? And then they're going to give us a basic instrumentation amplifier with a guard output. That means we're going to look at the AD522. This instrumentation amplifier have a data guard output built into the IC itself, all right? And by connect that to your shield, it will basically eliminate that, all right? That means that thing is already designed to do that. All right, that's all for today. Next time we'll look at 14.2. That means you can start working. You got half an hour to do some work in class, all right? And ask me any questions.